That's okay. I turned it on now. Thanks. Okay. So now we're back live. Okay, so basically what we want to do on a theory that has this fusion is we want to establish some identity between Hilbert spaces. So, for example, say that I look at a Hilbert space which is some sum over some product of two Hilbert spaces. So say I don't look at just this fusion. This fusion would be particle D going into particle, or the splitting, particle A and B. Whenever I draw diagrams, I don't want to draw lines. Just imagine the lines going upwards, unless I bend the diagram, in which case think of the line that's bent as being an antiparticle going upwards. Everybody with me? Okay. So what we want to do is not think of just splitting particle D into particle A and B, and this will have some index mu, where mu runs from, in this case, 1 to NABD. In this case, I'm going to split the particle D first into particle C and particle E, and then I split the particle E into particle A and particle B. So this is mu, and this is some other index nu, right? So this is a diagram that basically describes a process where you split this particle D first into E and C and then into A and B. Okay? But there's another, if I don't know what's going on here, okay, if you like mod that out, if you just have, you know, don't look at that part of the diagram. And if you don't look at this part of the diagram, of this other diagram, where this is D, this is A, this is B, this is C, then the outer legs are the same of those two diagrams, right? So basically you have outer legs which are exactly the same in the two diagrams. So there must be, in a unitary fusion category, a transformation between them which is unitary. So here let's just write this as mu prime and mu prime. Okay, and call this, what should we call it? F, this particle F. So this is first particle D breaking up in E and C, and then E breaking up in A and B. This is D splitting in A and F, and then F splitting in B and C. And just because the outer legs are the same, this should be expandable in this. And basically the moral of the story is whenever you see something that's got the outer legs the same, no matter what happens inside, okay, inside you might have braiding, which we'll do soon, etc. That diagram is still expandable as a sum of diagrams which have outer legs A, B, C, and D, with some, you know, it might be a complicated sum. It's not going to be expandable in just one diagram, but it's always expandable in that. So we know that this must be expandable in terms of this. And the expansion coefficients are called F symbols. And the way you write the F symbols is the following. Okay? On the upper, they've got many indices, which is the reason why this is a pain in the ass to solve it in terms of F symbols. Okay? Here show up the split space, so ABC. Here shows up the particle that was split. Okay? So that's the fundamental symbol. But now you've got, you know, for each of these combinations, for each of these particles, you've got indices. Okay? And the indices on the left, so you've got, it's really a matrix. And the indices here tell you that particle A and B split into E. And it tells you the fusion channels, mu, not the fusion channel, but the fusion, the internal degree of freedom of the fusion channel, right? Mu and nu. And here, it tells you that particle B and C well, particle F split into B and C, or B and C would have fused into F. So you've got F mu prime, nu prime. Okay, so this is kind of a composite index, right? Is that clear? So, we've established that you've got a fundamental symbol, A, B, C, D, which is called the F symbol. E, mu, nu, F, mu prime, nu prime. And if you're like, we'll be working with, up until, before I need to catch my flight tomorrow, we'll be working with theories with multiplicity 1. So I'm not going to, so these values can only take values of 1. But in general, they can take values, this one goes from 1 to n, a, b, e. This one goes from 1 to n, e, c, d, etc. Right? Yes?
Did you spend one of your guarantees that we can expand the left-hand side by diagonals?
Yeah, I mean, it's basically, the physical argument is that if you don't know what happens here, you might have braidings, or you might have loops or anything that's, just don't know what happens here. Okay?
It sounds like you do know, that symbol you...
Well, I do know in this particular case, but in more complicated cases, I don't know. For example, I'm not sure if I'll go through it, but I can expand some diagrams where I braid, where I take loops around and then split them into constituent particles. I can expand them, and I can still expand them in terms of something that's got only those particles in the end. So basically the problem is, so I know for this particular case, because I wrote this particular diagram, okay? But in general, whatever there's here and whatever there's here you ended up with ABC particles, and here you ended up with ABC particles. So it should be expandable in terms of there's only, in terms of Hilbert space. So this is just saying that for example, the Hilbert space of splitting D into E and C times the Hilbert space of splitting E into A and B is the same thing as a sum over F, and this is sum over this F mu prime, nu prime. Sum over F of Hilbert space of splitting D into A and F times Hilbert space splitting F into B and C. And this is just basically some sort of a consistency requirement that you don't need anything else in your theory to perform this splitting. So basically, whatever just because I reach the same particles in the end, A, B, C, starting from particle D, and there's just two ways of doing it, and these are the two ways, and they've got to be related. Okay, since the Hilbert spaces are the same, I can do it in one way or I can do it in another way. Yes.
So, can we say that if the total number of particles that is produced in the process is equal, so then we can relate them by this similarity?
Well, I mean, the total number of particles, I mean, depends what you mean produced. Of course, yes, of course, what you need is an intermediate state, just because, you have, basically Hilbert spaces are just splitting the Hilbert space for creating particle A, B, C coming from D is not, it's a sum over Hilbert spaces of creating, particle AE times VE, BC, right? So basically, whenever you've got, more than two particles, here my constituents of the theory are Hilbert spaces that contain just binary splittings. Okay, so whenever you got three symbols, you always basically split it. You always create one more particle and then kind of split it into two others.
Because if I want to end up with three particles, there is no other, and the splitting is only by two. There should be. I
mean, I can create other loops, but then I can create other particles, but then I have to annihilate them back. Okay, this is the simplest way I can create this. I could create other particles, annihilate them. For example, I could put a loop here. I could do this, but that would be just, I create two more and then I annihilate them. So in effect, you're right. Can only, the simplest way is just creating one more particle. Okay.
This expansion is not unique, right?
This expansion is not unique, and we'll talk about that.
So which also means the right one can be expanded in terms of the left.
That's right. That's right. And that's just the inverse of the F symbol. And that's what if you've got a unitary theory, that's just the dagger of that symbol. And that's right. Okay. And it's also not unique because these are gauge dependent. So, okay. Well, these symbols are not unique. Okay? All right. So these are called F symbols. And the point is, now look at what pane they are, or how many they are. There's, well, a priori, there's number of particles, 1, 2, 3, 4, 5, 6. Number of particles in the theory to the sixth. Of course, that's not entirely true because a lot of fusion channels are disallowed, right? So, for example, like it's not... This is kind of like a counting, which is not, it's just it's a hand-waving counting. But order of magnitude is number of particles to the sixth times some multiplicity of fusion coefficients to the fourth. So multiplicity, let's call it m, of fusion coefficients to the fourth. This is kind of like, this is a hand-waving counting. They're less than that, but because, not all the combinations of A and B can go into E, etc. So there's less than this number. But roughly, this is kind of like the way the way it scales. So it's a very high power, right? So for theories with higher multiplicity or with higher number of particles, this tends to be a mess. Okay, large number of symbols. Also, the way, just if you're like confused by how many indices I have, this E is just the fusion of A and B. So just when you see these two, just fuse them into E. And this F is the fusion of B and C. Okay? So that's how you look at them. Of course, B and C can fuse into many things. Okay? So there's some consistency relations because, A times B times C, they all have to fuse into D. So you can't just pick these, this F is not just any channel that B and C fuses to. Okay? So is that clear, or should we do like a small example? Brilliant. Okay. All right. So now, what I want to do is show you that these are not gauge invariant. So what I'm going to do is I'm going to take a state, and now let's focus on states with multiplicity 1. So I'm not writing this. Let's just focus on these for the moment. We'll talk about multiplicity greater than 1 theories in the end, but just through other methods. By the way, there's no computer program that can find these symbols for multiplicity greater than 1 in general. Even, basically people haven't been able to write down such programs because of the large scaling of these F symbols. And I'll show you how to find them. But first of all, I got to show you that they're not gauge variant. So I can take a state and send it. So in other words, make a state prime, make a gauge transformation on it, where this is a phase factor. So U, A, B, C is a phase factor. I can make that gauge transformation. Okay? So under that gauge transformation, is it clear that this F will change? Okay, so let's just find it. So under the gauge transformation, I have that I'm going to make a gauge transformation on this, on the left side. So the left side goes, so I have left side is equal to F times right side. I make a gauge transformation on the left side. So the left side goes into U, A, B, E. I made a gauge transformation on this. Then I make a gauge transformation on this. U, E, C, D times the left side. This goes into F prime, a new symbol, times the gauge transformed of the right side, which is U, B, C, F. B, C, F times U, A, F, D. Yeah? Is that clear? Okay. So there's a gauge transformation that F, yeah.
Splitting and not fusion. How did there be stars and things?
If you wanna take the diagrams, so this is how I define it. So there's no star. Okay, here. If I want to take the opposite diagram, there actually still won't be no star because of a scalar product that can be defined here. But this is a definition. So if you want to define this as the star or something else, we're welcome to do it. But I just define it like this. Or, you know, you can obviously make this gauge transformation if you want. I can redefine things as a star in any case. Okay. So obviously there's a gauge transformation that this F prime is equal to F, A, B, C, D, E, F times U, E, A, B, U, D, E, C over U, F, B, C, U, D, A, F. Okay? So first of all, these are not these F symbols are not gauge invariant. They change. Also, the other thing that physically we impose on the theory is that whenever either A or B or C, either of them is equal to 1, the F symbol becomes 1. And that's clear. That's just saying that if this is 1, I can just fuse. If I fuse to vacuum, I don't get anything. So this is just kind of trivial, and there's only one fusion channel then, right? Or is it clear that if either A or B or C is equal to 1, then the F will be just 1? Because there's no multiple diagrams to expand in. Yeah? Okay. Okay, so this is the second complication. So in general, if you just solve what I'm going to tell you now, which is the way to get the F symbols, you get an infinite number of solutions. Because they're subject to some gauge freedom. So basically you have to fix the gauge. And whenever you have to fix the gauge in some theories, you better just try other ways of doing it. Because gauge fixing is always kind of like a dubious thing, at least in my book. Okay, because it's annoying and hard. Okay, so these are not unique. Some of them are unique. So I'm not going to tell you about it, I'm not going to tell you about it because it's not interesting in terms of what we have to say. But some combination of these F symbols, and we'll see in examples, are unique. So for example, F, A bar, A, going into A with 1, 1. So this A goes into 1, this A and A goes into 1. This is gauge invariant. And you can just see that it's gauge invariant because if you plug in these constants here, this factor is 1. Okay? So when you've got an F symbol that's gauge invariant, that in a theory is a topological invariant. So usually they're called Frobenius-Schur indicators, or proportional to Frobenius-Schur indicators. And there's different Frobenius-Schur indicators. There's one that people really use, which is related to the R matrix, but there's Frobenius-Schur indicator of trivalent vertex. There's many things. But basically, what you have to think about is just, the fact that if you've got something that's gauge invariant in a theory, that's going to be a topological invariant of that TQFT. And you can find out in a theory, it's very, not easy, but it's only tedious. It's not, it doesn't consume your brain power, it just consumes your writing. You can find out which ones are gauge invariant, right? By just finding out the combinations of particles for which this quantity is 1. Yeah? Okay.
In your multiplicity, can you also have gauge in rotation?
Yeah. That's why I didn't do it. So by the way, nobody has managed to fix, with the exception of, I think now I've heard there is a code that fixes for 2 particles with higher multiplicity, fixes the gauge. But you can imagine that fixing the gauge for higher, because each of these will now become matrices. If I have multiplicity greater than 1, right? Because I'll just have another mu here, and this will have mu, and this will be nu here, right? So each of these will become matrices. So fixing the gauge in that sense, it becomes a real mess. Okay? And there's no method of doing it systematically so far. Okay, so now how do we find these F symbols? So I've told you, or how do we find this F symbol? So we first have to gauge fix them, and I'll show you how to gauge fix in Fibonacci and in semyon theory. I won't show you how to gauge fix in the Ising CFT because that's too painful. But you can go to Kitaev's paper and see how to gauge fix. We'll do that theory through another method. But let's see how you find these F symbols. So first of all, there's nothing that prevents me from splitting particle D in more particles. Okay, I can just split away. So let me just split away. Okay, so I'm going to split the particle D into A, B, C, okay, and E. Okay? So I'm going to split this particle like this. But I know that somehow there's another way of splitting it, which is D, A, B, C, and E. Okay? So somehow I must be able to go between this and this, right? Through just kind of making transformations on my space, making F moves. Okay? And it's very easy to see that there's 2 such paths you can go. Right? So there's a path which you first take this into here. You start with B. You make an F move on B. So let's call this, how do you want to call this? Let's call this M. Let's call this N. Okay? So first I make an F move here. So I do this. So this is D, this is A, this is B, this is C, this is E. Anything that I haven't moved, don't think about moving. So just leave these alone. Okay? And this is called this T, and this is going to remain N. Nothing changed here. Okay? Now do this. Again, move this one to this one. Okay, so go here. So here, what I've got now, so make an F move here. So now what I've got now is this. E, A, B, C. Okay, and D. And this is this T. Okay? And now call this one, what other thing do I have? R. Yeah? Are we good? And now take this part and make an F move here. And that leads you to this. Because I'm taking this part and making an F move here. And now let's write down what the things are in this diagram. This is R, okay? And this was T, so let's call this S. Okay? That's one way of going from one to the other. And here I've used how many F symbols? Well, 1, 2, 3. Okay? But you can see that I can start in a different way. I can start by first putting this here, making an F move here. Okay? So that's just this. Okay? So this doesn't change. It's still M. So I'm making an F move here. But this changes, so call it R, S, T. I use T, call it L. Okay? Alright, and now I can make another F move here and go from here to here. So I'm going back to this one. Okay? So I can make an F move here on this diagram. Okay? So I've just taken this, moved it this. And now I must make a identification. Why? Because this L was the fusion of C and E. But here the fusion of C and E is S. So this L is really equal to S. Yeah? Is that clear? I'll leave you like 3 minutes to sink this in while I write this equation in matrix form. In explicit form. God damn it. All right.
I have a question.
Yes.
So this state you wrote like A, B, semicolon, C is supposed to represent A, B fusing into C, is that correct?
Or C splitting into AB.
Yeah, so why is that, why am I supposed to think of that as a state?
Huh?
Am I supposed to like having a state A, B, and then over time goes to state C?
Well, so it doesn't go into state C, just as I explained so when you define a state, say I have 2 Majoranas, you can't just define the state by saying I have sigma, sigma. Those sigma and sigma have another quantum number, which is even or odd fermion parity. So the state is defined. It's not that it goes into time over some other state. You just project that state to a quantum number. And that quantum number is fermion parity. So you must define whether sigma, sigma are in this identities channel or in psi channel. There's no way of thinking, oh, well, I can go to both of them. Unless I do something with you just project that state to a quantum number, which is the C quantum number, basically. Which is, if I have 2 particles that can go into particle, when I fuse them, can go into particle C, D, E, okay? Yeah. Then I know which state they go in. Right? It's like basically having 2 Majoranas and putting them together. And, those 2 Majoranas came out of somewhere. And if that was a pure state, I know that they had a quantum number. Does that make sense?
Yeah, so you only need to go like one step back to all the quantum numbers, or you only need to think about, yeah.
No, I mean, in general, what you're required is that the full quantum number of so if I started here in particle D, if I fuse these back in, okay, if I fuse all of them, they still have to be in quantum number particle D. But, and we'll show this, if I do different things, so for example, we'll show this particular case, well, if I can get to it. If I create 1, 1 Majorana, sigma, sigma, so I create 2 Majoranas out of sigma, then braid them, then annihilate them back, like this. will show that the amplitude of the process 1, 1 goes into 1, 1 is 0. We'll show that the amplitude of the process 1, 1 goes into psi, psi is 1. But of course, if I fuse these two psis, they still have to go into state 1, just as if I fuse these two. So whatever you've got here and here, once you fuse them, has to be the same. But this is non-abelian braiding. If I started with 1, 1 separated, I braid them like this, just as I showed, and I end up with these, okay? So, particularly, what I do here influences the state of particles. So if I start with if I create particles A and B from something, the state of those particles, if I have other particles in the system, is influenced by braiding, okay? But the total state of the system is not, in the end, if I fuse them back together. Is that clear? Okay. All right. Any other questions? All right. So let's write this. Let's write this. This damn thing. Okay. So this one. Can somebody tell me what it is? What's the particle? What's this here? And what are the indices? Okay. And what is this one? Yes. Huh? ABS? Come on. And which? Brilliant. Okay. Now, I'm really lazy, so why doesn't somebody else tell me these indices? Come on. Just rev up the engines in the morning. What are these? Okay, yeah. I got confused. Okay, yeah. What is this? Come on, I don't need to put my finger on the board. It's impolite. Huh? N? Brilliant. Okay. MT? Okay, I'm just gonna write what you guys tell me, because then if you see a mistake, correct it. Yeah? It's called crowdsourcing. Yeah? Come on. BCE. My ear is waiting, but my brain isn't receiving. So, what is it? Okay. Huh? NR? Okay, I'm really not looking at what I'm writing, so just tell me. Is it? So which one is it? Huh? ATE, NR, okay. Yes. Now what? Goes into what? And what is this? Okay. And obviously there's an intermediate state that we have to sum, which is which one? Brilliant. You guys are the best. Okay. So that's called the pentagon equation. And we're going to solve that for the semyon case. Would you guys like to solve it now, or would you guys like to introduce braiding and then solve it afterwards? Ah, shit. Really? Okay. Okay. All right, let's do it for the semyon then. And I'm going to get...
Is it always S that splits into C and E? Like, couldn't it be a different particle that splits off into... Yeah.
So these you have to choose, okay? So normally really, so you just choose which particle you want to end up in. You see, like S doesn't show up here, so that's probably the source of your complaint. But you can choose which particle I can choose which diagram. So normally this would be a sum over S on the left side and on the right side. But I then identify the same S.
Okay.
So yeah, so some people write the pentagon equation as a sum, but that gives you less information than this. So you can, because you can then just project onto this guy. Okay, so let's do it for semions. I really want to. Okay, so semion is A times A is equal to 1. Okay, so I only have NAA1 is equal to 1. That's the only one that's, okay, non-trivial. And
Why is it a pentagon? Why is this the magic number for gauge mix?
Oh yeah, that's a good question. So, well, why it's a pentagon is 1, 2, 3, 4, 5. But the magic number is you can prove, and this I haven't proved, that, so obviously I can write down many other diagrams. I can put in 5 symbols, or 5 splitting spaces, or 6 splitting spaces, and I can come from 1 to 5 or 6. But you can, and it can go through different ways, right? So this is like the smallest number that you can go 2 ways in between 2 diagrams. But I can write a huge network of such, symbols. I can, start with whatever, 1, 2, 3, 4, 5, and 1, and I can get to 1, 2, 3, 4, 5, and 1 through more than just 2 ways. Okay? So the question is, does that give me new information? And the answer is no. You can prove that so you can prove that, I think that's called the MacLean coherence theorem, but you can prove that, but you can prove that this, if you know this, then all the other diagrams that you would get, all the other consistency diagrams that you would get from having more particles here, reduce to this one. Okay? Is that clear? All right. Okay, so let's do the semions. So it turns out that in this case you can just, so I'm going to do Fibonacci next. But in this case the situation is very simple. You can just show that the only symbol which is not equal to 1 is this one. Okay? So this is very easy. Why? Well, first of all, you have F, A, B, C, D, E, F. Okay? Every time this guy is 1, this guy is identity, one of these guys is identity, this F symbol is 1, as we showed. Okay? So the only thing that's going to be non-trivial is AAA. Right? Okay, but AAA, what can it fuse into? Well, A times A, whatever it is, this symbol here has to be the fusion of these 3, whatever happens in between. A times A fuses into 1, which times A can only fuse into A. So this has to be A. And A times A, this symbol is just fusion of A times A, and this symbol is just fusion of this A times A, so it's 1. So this is the only one that's not non-trivial. Is that clear? Okay. So then, what you do in this equation, you just pick out A, B, C, E to be equal to A. Yes, okay. So you just pick out, so you look at the pentagon equation with A. Okay? And you pick D, obviously, then D also has to be, you pick D equals to A. Let's see, D, yeah. So you pick also D is equal to A. Actually, hang on, I'm kind of confused. No, you don't look at, sorry. Shit. So A times A is 1, times A is equal to A, and this is 1. So that doesn't work. Let's just see which. Hang on. Let me just see which one. Okay, yeah, so CE. Okay. All right. Well, let's just do it without this. Okay. Let me pick. I'm going to pick A, B, C to be equal to 1. And I'm going to have F, so pick A, B, C is equal to 1 first, and rewrite that equation. M, A, E. You see, this is like the point about like this stuff becoming annoying. And S is times F, A, S, D. We're just going to pick these two equal to 1. M has to be 1 now, because it's the fusion of M and M. MR is equal to sum over T, 1 and A, of F, A, N. But N is the fusion of A, N. So N has to be equal to A. Okay? So I have put A, which is equal to N. This is M. All right, times F D of A C E of N R, but N is A. So let me put the A here. So N is A. AR time F B C E of R TS. All right. Now, it's fortuitous that M is equal to 1 because M times A had to be equal to A, right? This symbol is just fusion of M times A. So M has to be equal to 1. Okay? Yeah? And since this symbol's got a 1 in it, okay, this can only be 1 or 0. Okay? So now let's see. Oh, B is 1, right? So A, B, C. B is 1. B and C. So A, B, C is 1. So this is AA. So if this is AA, then T is equal to 1. Right? Because it's A times A. So T is equal to 1. So I can't sum anymore. Okay? T is equal to 1. Okay? And this is AAA, and I'm not writing these symbols no more because I know they're 1, 1. Okay? So this is the guy that I need to show what it is. And obviously, since this has got a 1 in it, then this is either 0 or 1. So the only thing that I need to find FAAA is to now particularize to E equals to A. Yeah? So I'm going to make this E equal to A. Where else have I got E? Well, I've got E here. So I'm going to put A here. Okay? Now A times A goes into 1.
There's only 1 in the middle left.
Thank you. Thank you. Okay? Now A times A goes into 1. 1 with 1 goes into 1. So D is 1. Yeah? R is equal to A times 1. So R is A. And A times A is equal to 1, but S times A times A has to be equal to 1, so S has to be equal to 1. Yeah? Everybody agrees? That's lovely. Okay. And R is equal to A from here. So S is equal to 1 and R is equal to A. Okay? Alright. So now we're done. Each of these have 1 in it. So this left side is 1. This has 1 in it. So this is 1. Okay? So I have that this squared is equal to identity. So I have two solutions for the fusion equation. One of them, which is the trivial solution, which is always have, which is just ones. Well, I'm not going to. I have one non-trivial solution that actually matters, which is FAAA 1, 1 is equal to minus 1. So that's the only solution to the fusion equation for semions. And that minus 1 is important because we'll find out that the braiding squared is equal to that F symbol. Okay? So, I mean the exchange squared. So then, that means the exchange is equal to I, which means that they're semions. So that's how it goes, okay? So I want to get to there. I want to get there. So let's. So I'm going to hurry up a little bit, okay? So everybody happy with this? Yeah.
At some point you choose to take E or A.
I didn't.
There is no constraint at this moment. Was it?
There's no constraint here. You can here between left side and right side. You can choose whatever M, C, E, A, B, S, D you want, as long as the fusion rules are satisfied. In other words, M, C, E doesn't go to D, then this would be 0. Okay? But there's no constraint. And that's actually not, there's both a problem and a blessing, in the sense that this is highly constrained. This is a highly constrained system. That's the blessing. The problem is, it's a nonlinear equation in number of particles to the 6th times number of fusion in degrees of freedom to the 4th. Because I would have indices here. So everybody realized that this is just the pentagon equation for no indices here. Right? Otherwise I would have, if I would have multiplicities, I would have another index here. So this would kind of, in the notes it's written up. Okay. Yeah. Why is what? No, it's just a trivial solution. It just has nothing non-trivial about it. Okay. I mean, it just has all the braiding faces equal to 1. Everything equals to 1. You know. Well, it really means that I should identify this particle A with a vacuum, because it's got nothing special. You know. By the way, this particle A, what's the quantum dimension of this particle A? Okay. So that solution. So usually the solution where the F symbols and everything is 1, we disregard it, because if topological spin is also 1, if things are also 1, then you just identify that particle with a vacuum. So it really doesn't make any sense to say I have 2 particles if I can't distinguish. Okay. So there's one fusion category solution to the semyon fusion rules. All right. Another thing that I want to show you very, very quickly is how to define the quantum dimension in another way. So usually the quantum dimension is not defined like that unless you assume unitarity in your theory. But you can define the quantum dimension by making the following diagram. I take the particle A, I move it like this, then this is particle A here, which goes back in time, so it's really particle A bar here. This is particle A, and this diagram really means that I have vacuum here and vacuum here. But the vacuum lines I can just erase. So this diagram is equal to a phase times this, right? Because even though I bent it, it still goes up, right? So physically it's equal to a phase times this. But this, I'm going to make an F move here and bend this from here to here. So I'm going to write the diagram, but you tell me what F symbol it's got in it. So and what's the F symbol? So these are kind of like ones when I draw them. So what's the F symbol that I need to apply? Huh?
A bar, A, and 1.
Okay. But what is this? This is time. What is this? This is just this times what? Exactly. So now we've discovered that dA is the absolute value of F A bar A 1 1 to the minus 1. Okay? So from the pentagon equation, you can just it's good to teach. You can just get the F symbol and take its absolute value. In fact, it's going to be, we can prove that it's plus or minus 1 times dA, and that plus or minus 1, it's a gauge invariant quantity because this is gauge invariant. And so this phase is really gauge invariant because FAA bar is gauge invariant. And that's called the Frobenius-Schur indicator, but I'm not going to go through that. But this is the definition, really the category definition of the quantum dimension. It's not the eigenvalue of the highest eigenvalue of the N matrix, but they're the same in unitary theories. Okay, so now I'm done with any questions. I'm done with fusion. I want to go to braiding. I want to prove several things. Actually, I have to go a little bit faster if there's any examples to be given tomorrow. Okay. Any questions? So now I'm going to do the following. I'm going to take two particles, create them from some other particles, and then braid them. So I'm going to do the following operation. This is some operation which has got a matrix representation. Like this.
Andre,
Yeah.
can I ask a question?
Sure.
So the theory, you can define the theory using the ends. The ends define the theory. But given a theory that has a certain fusion rules, you can find the S. Difficult as it is, but you find the S.
There might be more than one solution.
Okay. But then, even with more than one solution, there will be relationships between the quantum dimensions that you obtain from the ends with the S. So
Yeah.
it has to be F consistent.
Yeah, if the theory is unitary, there will be. So, yeah, exactly. It has to be, so all these are consistency relations. There's theories for... So, for example, you can prove... Well, it's been proved, but it's very hard, so it's been proved by math people in language that I don't understand, that A times A equal 1 plus MA, where M greater than 1, has no fusion solutions, no unitary fusion solutions. So I'm going to prove easily that it's not modular. But that's a much harder constraint that there's got no fusion solutions. So fusion solutions you can have even if the theory is not modular. But basically, you know, the F symbols already constrain the theory quite a bit.
So can you repeat what is modular unitary?
Yeah. I'll repeat it when I get to the S matrix. So modular for our purposes is going to be the S matrix is going to be unitary. So it's not going to have determinant. It's going to have determinant. Absolute value of determinant 1. That's going to be for our purposes. But unitary fusion, it just means that the F matrix is unitary. So if I have the F matrix of A, B, C, D as a function of these indices, is unitary. And we're going to use that to obtain the Fibonacci. So if you don't use unitarity on the Fibonacci, you get more solutions. If you use unitarity on the Fibonacci, you get just one solution to the fusion equation, to the pentagon equations, and which splits into two solutions of the braiding equation. Okay, so what I'm going to do is I'm going to start with, so this is something that does this. I start with particle C. Okay, and I just exchange. So this is just exchange. And this equation tells you that this, and I'm going to add indices now. This is sum over nu, R, A, B, nu, times B, A, R, A, B, C, mu, times nu. Yeah. Very good, thank you. Okay, so that's how we're going to define the braiding this matrix. All right. So now there are several things that I want to do. First, I want to define a topological spin. Which is a phase. It's a phase that's a topological invariant of the theory. And it really assumes that the particle, if I take a particle A, I can make it into a ribbon. So instead of having the particle A point, I make it into a ribbon. What I do is I take the ribbon like this, flip it around, and then go back into the positive time direction. And this corresponds to a 2π rotation of the ribbon. And this is just, if I had rotational invariant, this is e to the I 2π times the spin of the particle. But it's a phase. And the way I'm going to define it is the following, physically. I'm going to say take this particle. Let me define it in the same way. Okay, take particle A. And this is a phase times A. Okay? And that phase is the topological spin.
What's the top equation?
What's
the top equation?
This?
No, top, above.
This?
Yeah.
This is an operator. This is a matrix. This operator just does this. This is the exchange operator. Okay?
Why do there C index and why are the indices downstairs on the left?
Now, this is an operator.
Okay.
When it acted on a state, it's got a representation which depends on this. This is a matrix, this is an operator.
So that operator doesn't care that.
I mean, the operator's got matrix elements. When you put it around C, it depends on C.
Okay.
But that operator is just the operator that exchanges two particles.
Okay.
Irrespective of where they come from, it's an operator. Its matrix depends on...
Yeah.
Yes? What's that?
In the first line, I would have had VAC, is it symmetric or?
Is it symmetric? No, it's not symmetric. They can differ by signs, and they can differ by phases actually. So it's not symmetric. Let's see. RAB. Okay. Just think of it like that. Okay. Is this better? Okay. So this is a state this is the state that ends up with R and B switched. So it's got to be, well, okay. All right. So this is a topological spin. So let's find out what this thing is in terms of R matrices. Okay? So we can find out what it is in terms of R matrices. How do we find out what it is? Well, we're just going to trace out the loop. So we're going to take this and add to this on this side with A bar going like this. Okay? So A really going like this. I'm going to do it here too. Okay? What is this number? Huh? So theta A dA is equal to this. Okay? A. Okay? But now I can transform this into this. Elongate it like this. Same thing. I'm going to introduce a set of states here. A full set of states here. And here I'm going to have that normalization factor, square root of whatever. Let's just call it a normalization factor, because it'll die in the end, okay? Because you remember this is the square root of dA over, okay? this normalization factor times this. So the thing is, why can't I just switch them with an R matrix here, these? I don't know what fusion channel these guys are in, right? A and A. So I have to insert an identity, fuse them, and then change them, right? So I insert an identity, so I insert this, I have A going to C and mu here, and this is AA, well, A and A bar really, but no, A and A, sorry. Okay, and these go back here, okay, and this goes here, and this goes here. Okay, this is A. Yeah? So now I know what fusion channel they are. So I'm going to swap them. This is equal to sum over C mu, this norm. This norm depends on AAC. It's the square root of DC over DA. Okay? Times RAAC times this. Okay? With this is mu, and this is nu, and this is nu here. Is that clear? Sorry, this is still mu here, and this is nu here. Yeah? Because this is the same thing as this, and I acted R here, which R comes with a this was mu. Yeah? So this now becomes, what I'm going to do is I'm going to take this and move it on this side. Okay, do it like that. So you can think of it as taking it in the other dimension and moving it like this. Okay? And this is mu, this is nu, which this guy is the same as norm times RAAC of mu times C going like this. I'm just extending it like this. Rules of the game is I can do pretty much anything if I don't have to keep ends fixed. Okay, this is nu, this is mu. But norms times this is identity, because this is 1 over the norm, the bubble, remember? So this is just sum over C mu. This bubble here is delta mu nu. So first I cut this. So it's R sum over mu C A. So this is delta mu. So I have the trace of this matrix. Okay? Times this. So this is sum over C. What is this number? Okay. Yes. Sorry, can you say that again? Just louder. If I write the what?
You see, on the first line, after the third equal sign, there is a sum of something. Now, the sum of the thing just after the sum.
This?
Before that, before R, after the sum.
The norm.
That one.
But this bubble has 1 over this norm. Basically, norm can't really enter things non-trivially, right? It has to cancel out. So this bubble has 1 over the norm. All right? Okay, so what we found is that knowing the R matrix, so this trace is over the internal indices of this fusion. This splitting channel C goes into AA has fusion indices going from 1 to NAAC. So this trace is over those indices, but if I have multiplicity 1, it's just that. It's just this number. Okay, so it's sum over all the particles in the theory that where AA goes into C. Okay? Any questions? Because I'm going to go to another thing and prove something more. So I'm going to end with the hexagon equation today, because we'll we'll find the solutions to the hexagon equation for several models. So next class is going to be only examples and how to use this. But I want to do the Verlinde formula today. Okay? And there's an issue because I'm running slow, so I can't do Waffa's theorem, which would actually show us that the topological spin is, so topological spin is e to the I 2 pi SA, and SA is a rational number, and you can prove that it's a rational number, and that's called Waffa's theorem. But I'll try to go through it, but I don't know if I'll have the time. It's going to be in the notes, though. Okay.
Erase that.
Okay. So what I want to do now is I want to obtain an important identity.
The topological spin is theory dependent because
It depends on particle A. It's a topological spin of particle A, and it's different for different theories. So I haven't told you how to I just defined this matrix. I haven't told you how to obtain it. Okay? But you obtain it from the same set of consistency equations, pentagon, but you get a hexagon equation in that case. But so far I don't want to obtain it like that. Because I want to go, you can define S matrices and things like that without knowing anything about the hexagon equation, in a sense. I want to obtain the following identity. RABC RBAC is equal to theta C over theta A theta B. Okay? And I need to be a little clinical here. And to obtain this, I'm going to look at the following. Graph. I make particle C go into particle A and B. Okay? And now I'm going to make particle A do something like this. And particle B also, let me see exactly which. Shit. Okay, I'm going to make particle A do, it's basically like do this. Okay, and make particle B do this. Okay? And I'm going to combine them back into particle C. I know they have to go into particle C because they came from particle C. Okay? This is particle B. Yeah? Alright, well, I'm going to express this graph in two different ways. First way, I'm going to make this line elongated. Like this, right? So first way that I'm going to express it is I'm going to unwind this and move it into the C. So I want to make sure, if you guys agree, that this is the same as this. So what I've done, you can just take this thing, move it like that, right? Put your fist in the middle, take it, grab it around, and it'll get here. Yeah? Is that clear?
No.
Don't let this, just hold on tight to this. Imagine this is yeah. Just hold, I don't know what it is really. Imagine something. Okay? Put, and now imagine these are wire. These are like, it's a thread. Okay? And now roll it. Just pull it like this. Thread of limited length. Pull it like this. It's going to get to this. Is that clear? Just think about it. If you pull it like this, it's going to move it up, move it up. This. Oh, come on.
Slide under each other.
Yeah, these are both on top of each other. It's the fact that both of these are on top of the lower ones. Just put it here, pull the thread up, and then it'll come out to this one. Yeah? Is that clear? Brilliant. This is particle C. So this is theta C times this. Okay? Yeah? That's one way of expressing it. The other way of expressing it is by doing nothing of the sort that I did before. First, I used the fact that topological spin is theta times this in here. and rewrite this as the following. Okay? So, sorry, this is B. Okay? You agree? I just took it out of here, right? Yeah? We agree, right?
No.
Oh, come on.
No, it's okay. Just keep going. I trust you.
No, don't trust me. It's a horrible thing to do. It'll get you nowhere. This is B, B, B. If I pull it out, it just looks like this with a B. I'm going to take it and say that this is equal to theta, which is topological spin. This is the definition, times the straight line. This gives you a straight line here. This straight line is just this. Trust me. Okay, this one I'm going to do something more unkosher. I'm going to take, well, no, everything is kosher, but I'm going to take this and move it out. Take this thing and move it on this side. So let's see how it's going to look. Okay, so what I am going to do is okay, so all that I did here is I took this line and moved it on this side, and I took this line and moved it on this side. Okay, so what you do is you take this, move it here, and you take this and move it up. Okay, and what happens is that this, you see, the links don't change. This goes down like this. This is linked with itself. A is linked with itself, so that's this. Okay, and this goes up, and that's this. Yeah. Brilliant. So this is theta B. I keep theta B. Now I get rid of theta A. Yeah? So this is theta A, theta B times C B. A, B. Yeah? A, B, C. By saying that this, which is A, is equal to theta A times the line. Yeah? Okay. But what is this? This is just R. This is A, B, A, B. This is just RAB, RBA. So I have that this is equal to theta A, theta B, RAB, C, or RCAB. RCAB, RCBA. Yeah? So that's equal to that, to this. So I times this bubble. So this is equal to this, and I've obtained this identity. Yeah? Is that clear? Okay, so that's an important identity. And we're going to just power through and do the S matrix. Can I erase this?
Yes.
So the S matrix is very important because it tells you what phase two particles acquire when they wind around each other. Okay? Unfortunately, the R's are more important, at least to my liking, because it tells you directly how particles braid and what state you get. But the S matrix is easier to get. Okay. So I haven't defined what the R's are yet. Okay? And I haven't defined what the thetas are yet. But we're going to find out very, very soon. So everybody's happy with this? We've got like 10 more minutes. Okay? Alright. So now, what I'm going to define is the following. So this is called the S matrix, and this D is called the total quantum dimension, and the reasons for defining it so far are very non-obvious, and they will remain non-obvious, but the reasons for defining it like this D is sum over all the particles in the theory, dA square root. So we know how to obtain dA is easy, so we know how to obtain D. The reason for defining it like this is so that you make it unitary. Okay? And I'm going to prove that SAB, I'm going to work only with theories where a particle is its own antiparticle, but in the notes everything is done properly. So it's 1 over D, sum over N, A, B, C, theta C over theta A, theta B, times DC. I'm going to prove this relation for the S matrix. So obviously this matrix just tells you that I take a particle A around particle B and then go back to the vacuum, right? There's just the phase, yeah? Everybody with me? Or does everybody check out? Who's still with me? Because we're going to Iraq. Okay, so who's left me? Don't leave me. It's an awful thing to do. Okay. Okay, so how do you prove this? Well, this is actually very easy to prove. Okay? The way you do it is by inserting an identity here. So we're going to do the same, so what we did before. So I'm going to do this. What's up?
How about the fixing for these R and S matrices? H fixing fix. That's so the R matrices to the hexagon equation. That's an important question, and it's not easy to answer. The F matrices appear in the hexagon equation. So the R matrices are related to the F matrices. So you can't solve the R matrices first and then solve the F matrices. You have to solve the F matrices, the pentagon equation, and then the R matrices. So normally you have to gauge fix the pentagon equation, and then normally you remain with no degree of freedom left, and then you solve the R matrix. However, I think it's been shown, at least for unitary theories, that you can alternatively gauge fix the S matrix, the R matrix, and that also gets rid of all the gauge degrees of freedom that you have. But that's only for unitary theories. You can show that, and I think Parsa showed that in an unpublished stuff. So, anyways. When you mentioned the non-unitary theories, should we care about these? Or?
Yeah. When I mentioned we shouldn't care about non-unitary for the purpose of this class. I mean, I care about them just because, I really have nothing better to do. Okay, but for the purpose of this class, let's not care about them. But of course, they're important to understand what's going on. They might describe phase. They might describe phase transitions in quantum Hall states. Let's just not worry about whether they're physical or not. Let me worry about them, okay? In the back of my mind. All right, now we add an identity here, okay? So we do the same. It's 1 over D times sum over C times an identity, and then now we have this thing here times a norm. I'm not going to write the norm. You can write it down, or you can just look at the notes this part is already, I think, in notes that I sent to Mark, but I'm going to send new ones today, so by tomorrow you can look at them. So the sum over C and mu of this, right, I just inserted identity, times some norm, which I don't care. It'll cancel in the end, so let's forget about it. So this is 1 over D, sum over C, times RAB squared, so RAB, RBA, which is that. Okay? I'm just doing it, very cavalierly, this norm, times
this C going into this, okay, because I've gotten rid of the braids. This is RAB, RBA, but by this formula, I'm just putting it as C. There's a coefficient here, so this norm. This is 1 over D, sum over C, theta C over theta A, theta B. This is A, B, C. C A, B. I'm just taking this, putting it like this. A, B. Okay, I'm going to take this around and make it this, times norm. I'm going to take this around and make it this. AB. Then the norm times this gives you identity times the number of ways A and B can fuse into C. That's 1 over D, sum over C, theta A, theta B, times number of ways that A and B can fuse into C. Because if A and B can't fuse into C, that's got to give you 0. So obviously you've got to have this thing if I just sum over C. Okay? Because if I didn't have this thing, then I could sum over all C's, even if A and B didn't fuse into it. So that can't be correct. So I have to have this, and mathematically it works. Times this, C, because I've just got this. So this is DC. Okay? Is that clear? How many people feel completely like I've done I've done a caca out of all this? How many people feel how many people are still with me? Oh wow, you go to war with half. I can't not erase because I got to write somewhere. Okay. Yes.
How come people see over feeling or
How come? Yeah, normally I would have to just pull it like this, or make this, and pull it like this, which would give you a factor of theta A star. But theta it has got more. So just think of it. I don't want to get there because I haven't, to prove that theta A is complex and it requires bending. So I don't want to get into bending. So just think of it as taking it around in the other dimension and moving it like that. Although that's not entirely correct. Really what you should do is you take this B and you move it like this and you create two loops. But one is theta A, one is theta A star. They cancel. Okay? But just think of it as kind of doing this. Okay. Yes?
So when you put C in between, in the second part of the last equation, what is it that constrains that on the top side, A and B in the right order?
This is also A and B. Because the identity is A, B, C. It's not BA because that will involve an exchange. That will grab another phase. Okay, very good. Okay, Ilya, I'm going to erase this. So now we're going to prove the Verlinde formula, which will make everything... beauty will come out of the board. And then we'll stop. And then next lecture we'll use all these things that we've learned. We'll do the hexagon equation and use all these things that we've learned. I can't do Vafa's formula, but that's life. Okay. So now I claim the following thing.
Can you write the name of the Verlinde?
Verlinde formula, yeah. Well... First of all, S1x is equal to what? What's S1x from that figure? Come on. Yalla. What is S1x from that figure? Huh? Dx over D. Right? Okay. Then I claim this is this. Sorry, this is this. So this is particle X. Of course, this has to be expandable into particle X. Okay? and anything that, so it's a Hilbert space, just a particle X, because I haven't split it or anything. So how do I prove that this is true? Well, I'm just going to, this is not a proof yet, so I'm just going to do this, okay, with an X particle. Okay? What is this, then? SAX is equal to number times SAX times D, right? And I defined it with a quantum dimension, with a total quantum dimension. What is this? Okay? So this number, which is this, is equal to SAX over dx over d. So it's equal to SAX over S1x. Okay? So I'm just going to take 5 more minutes because this is important, and so just really use your, it doesn't matter if you don't listen to the other talks. Just use your last energy to understand this. Okay? Is that clear? No. Okay, well that's bad. So I claim that this AX is equal to a constant times X, right? Because I didn't know what's here. I have X goes, so it's got to be a constant times X. Okay? What is this constant? How do I find it? I'm just going to take the scalar product of this with X. Then now this is dx, is just a loop. Okay? So this is dx. What is this? This is AX. But that's the definition of the S matrix. This is just SAX times D. Yeah? So this constant has to be SAX over S1x, where S1x is dx over D. Right? So the point is the first column of the S matrix is just the quantum dimensions, well, over the total quantum dimension. Alright, so finally we're going to prove the Verlinde formula, which is a very important formula in both conformal field theory and this kind of thing, this TQFT. By the way, the difference between CFT and TQFT is if I had a CFT at the edge of this TQFT, this theta A is e to the I 2 pi times the conformal dimension of the H. So you can see that the TQFT doesn't know anything beyond the conformal dimension mod 1. Okay? But that's for people who know CFT. Anyways, let's just focus on this. And now what we're going to do is take particle X and put particle A and put particle B here. What is this? Well, this can be expressed in 2 ways. First of all, I cut it here. So what's this thing? This is SAX over S1x, and this is SBX over S1x. Okay? Yeah? And now what I'm going to do is I'm going to slide this, I'm going to make this string, this loop, slide it into here. So this is also equal to this. You agree? I just made this loop small, put it here. Yeah? And now we're going to introduce our most used thing in what?
I'm not sure when you can use this third dimension or not. Sometimes you leave loops one over the other, or in 2D, 3D. What are the rules of the game?
So the rules of the game is as long as you leave the ends unscathed, like you don't move the ends, and as long as you don't, I can't do this. So for example, this one, I can't just if there's a loop, and I can't pull it through because there's a knot in it. Right? This one I can't, this one is not this. It's just theta A times this. It's a phase times that. Anything else, you can just pretty much take loops between. If they're not linked, you can take them. You can separate them. Okay, that's called. And you can rotate graphs as long as you don't rotate the ends. So this one I could have drawn it like like this, right? I've drawn it like this, etc. Another loop here. Sorry, X. That's with the same. So I can rotate things. That's called isometry, basically. So as long as I don't kill, as long as I don't get rid of knots, I can do it. So obviously this loop is not linked with this. So by moving it here, I maintain the same linking number with X. So I'm fine. So now I'm going to introduce, God damn it, I'm going to introduce an identity in between these. Okay? Sum over C, A, B, C. Okay? And there's a norm here that I don't want to look at the norm. Okay? C and mu. The norm doesn't depend on mu. The norm is just d square root of dc over dA dB. And this is X. So now what I'm going to do is I'm going to take this around. So this is the same thing as this norm, which is square root of whatever. Everybody knows what the norm is, right? We talked about it. Okay.
There's a nu also, right?
But the norm doesn't depend on mu. But there's a mu here. The norm is just square root of dc over dA dB. And it'll cancel. Okay? Okay, so I'm going to do this. All right? And now this norm times this. So this bubble is just delta of this time delta in these indices. So this is mu, delta, and this is C. The delta of C is already found. The delta of mu is already found. But so this is identity. This times the norm is identity. But what's going to show up is the number of ways, that's the sum over mu, is the number of ways in which A and B can again split into C, or in which A and B can fuse into C. Because if A and B can't fuse into C, I got to get 0. So this is NABC times this. Sum over C. So that, can somebody tell me what that is? What's that graph? What's that graph? S what? This is not yet the Berliner formula, but in 1 minute it will be. S1x here goes to S1x here. Okay? Now this is very, very powerful. It again tells you that the S matrix diagonalizes the fusion symbols. Okay? Clear? So if I define this as a matrix, if I define NA of BC is equal to NA BC, then if the S matrix has an inverse, and the S matrix is if the S matrix has an inverse, so if it's unitary, it'll have an inverse, and that's where you use unitarity. So that's called a modular tensor category. If it's an inverse, then I can just apply the inverse on this side and obtain that NA is the S matrix times the diagonal, which depends on A, times S to the minus 1, where the diagonal A is a matrix, dA is a matrix of Mn, which is diagonal, which is just SAM over S1M times delta Mn. So this is clear from here, right? This is just matrix times vector is equal to vector times eigenvalue. Okay? So then I can just this is just the projector representation of this matrix. right? If I have this eigenvalue equation, this is a very important equation. Why? Well, first of all, we looked at the beginning and we saw that I told you that the n matrix has common eigenvectors. The n matrix has common eigenvectors. Right? 1 second. The S matrix has common, the n matrix has, all the NA matrices common eigenvectors. You can clearly see it here because each n matrix is diagonalized, it's got the same eigenvectors. Okay? So NA obviously commutes with NB, just because D is diagonal. But moreover, even the more important thing is that even the eigenvalues of the N matrix are the S matrix, are part of the S matrix. Okay? So even the eigenvalues is not just that you have commuting matrices, which is the only thing you learned from that the NA matrices are commuting, which is the only thing you learned from fusion associativity, but also that its eigenvalues are the same as the S matrix. This imposes a large number of constraints on the system, which we'll do examples next time. All right, so
the Bernoulli formula is this one?
the Verlinde formula is that one. This is Verlinde formula. And it's obviously a very, we'll show how it basically fixes the theory. Okay? Well, that plus the T matrix. So that formula plus the topological spin fixes the theory. Okay. Yeah. Huh?
Where's T matrix?
T matrix is not here. T matrix is just theta C on the diagonal. That's the T matrix. T matrix is just the matrix of the topological spin. Okay, so if you've got questions, since we need a break, just come talk to me and just over coffee.